Hello?
Hello.
Hi.
Well, so far, you're the only one here. I'll wait just a couple more minutes. Did you have any questions?
No, not so far.
Okay. All right. You getting kind of
Oh,
bored at home?
yeah, a little bit.
Yeah. Yeah, I hear you.
But do we have a quiz coming up at all?
No, I haven't figured out what I'm going to do with the quizzes or the tests at this point. I will definitely let you know, though.
Okay, sounds good. Thank you.
Yeah. Okay. Well, looks like it's just about time to get started here. Oops. Another one here. Okay, so I think we looked at problem number 13 yesterday. Do you guys want to look at it again or just skip it or don't care?
Can we look at it again?
Absolutely. Okay, so problem number 13 says you have a key ring with 5 keys on it. Part A says one of the keys is a car key. What is the probability of picking that key? The probability of picking the car key is just the number of car keys divided by the number of keys. There we go. Sorry about that. So the probability of picking a car key is the number of car keys divided by the total number of keys, which is 1 out of 5. And then part B says 2 of the keys are for your apartment. What's the probability of selecting an apartment key? The probability of selecting an apartment key is the number of apartment keys out of the total number of keys. And there's 2 apartment keys out of 5 keys, so that probability is 2 out of 5, 2/5. Part C says, what is the probability of selecting either the car key or an apartment key? So the probability of selecting either a car key or apartment key is the number of keys that are either for the car or for the apartment out of the total number of keys. And so that's going to be a probability of 3/5 because there's 3 keys that are for the car or apartment out of 5 keys. And then part D says, what is the probability of selecting neither the car key nor an apartment key? And remember, there's 5 keys and 3 of them are for either the car or the apartment. So the probability of selecting neither the car key nor the apartment key is the number of keys that are not for either the car or apartment out of the total, and that'll be 2 out of 5. Problem number 15 says, what is the probability of getting yellow on each of the following spinners? And spinner A has 8 sectors, that are all equally sized and shaped. And so the probability of getting yellow is the number of yellow sectors out of the total number of sectors. And since there's 3 yellows out of 8 total, that gives us a probability of 3/8. And part B says now we're looking at this spinner that has 6 sectors that are all equally sized and shaped. So the probability of spinning and hitting yellow is the number of yellow sectors out of the total number. And there's 3 yellows out of 6, so that's 3/6 or 1/2. Problem number 16 says, a die is made that has 2 faces marked with 2s, 3 faces marked with 3s, and 1 face marked with a 5. If this die is thrown once, find the following probabilities. Part A wants us to find the probability of getting a 2. So the probability of getting a 2 is the number of faces that are marked with 2s out of the total number of faces. We know there are 2 faces that have 2s on them, and then to find the total number of faces, I'm adding up the 2 faces that have 2s plus the 3 faces that have 3s plus the 1 face that has a 5. So that gives me 2 out of 6 or 1/3. Part B is asking for the probability of not getting a 2. So the probability that we don't get a 2 is going to be the number of faces that don't have 2s on it out of the total number of faces. And there were 6 faces, 2 of which had 2s on it. So that means there must be 4 faces that don't have 2s. So that gives me the probability 4 out of 6 or 2/3. Next, part C, the probability of getting an odd number. Okay, that's going to be the number of faces that have odd numbers out of the total number of faces. And an odd number for this example is going to be getting a 3 or getting a 5. And there were 3 faces that had 3s and 1 face that had a 5. So that is 4 faces out of the 6 faces. And that reduces down to 2/3. Part D is the probability of not getting an odd number. So the probability of not getting an odd number, that'll be the number of faces that don't have odd numbers out of the total number of faces. And the faces that don't have odd numbers, those will be the faces that have a 2 on them. And there were 2 of those faces. So that probability is 2 out of 6, which reduces down to 1 out of 3. Next, we're going to look at problem number 17. It says a card is drawn from a standard deck of cards. Find the probability A union B in each part. And I've got the little picture from the book that just shows us the cards in a deck of cards. Part A has event A, which is getting a black card, and event B, which is getting a heart. The probability of A union B is the probability of getting a black card or a heart. Okay, so anything in these bottom 3 rows will be in that event. So we're going to count the number of cards that are black or hearts on top, and then the total number of cards on the bottom. There's 52 cards in a deck, and there are 13 clubs, 13 spades, and 13 hearts. So that gives us a total of 39 on the top, and that reduces down to 3/4. Part B, we have event A, which is getting a diamond, and event B, which is getting an ace. So now we're thinking about getting a diamond or getting an ace. So the probability of A union B is the probability of getting a diamond or an ace. And so that's going to be the number of cards that are diamonds or aces out of the total number of cards. We've got 13 diamonds, which includes one of the aces, and then 14 for the heart, 15 for the spade, 16 for the club. So that gives us 16 cards out of 52, and that reduces down to 4/13. Next, we'll look at part C. Event A is getting a face card, and event B is getting a spade. Remember, the face cards are the jacks, the queens, and the kings. So the probability of A union B is the probability of getting a face card or a spade, or both. This is going to be the number of cards that are face cards or spades out of the total number of cards. So first we can count the 13 spades, and then we have 3 face cards that are clubs, and 3 face cards that are hearts, and 3 face cards that are diamonds. That gives us 22 cards. So we have 22 out of 52, and that simplifies to 11 out of 26. Next, part D, we'll look at event A is getting a face card, and event B is getting a 7. So we'll find the probability of A union B. That's the probability of getting a face card or a 7. So now we need to count up the number of face cards, the number of cards that are either face cards or 7s out of the total number of cards. So we have 4 7s and 4 jacks and 4 queens and 4 kings. So that'll be 16 cards out of 52 cards. And that will simplify down to 4/13. Next, we'll look at problem number 18. It says, with the spinner, in example 11.2 part C, we spin twice and record the color on each spin. So the spinner looks like this. There's 4 sectors. They're red, blue, green, and yellow. And then it says, for this experiment, consider the sample space and the following events. Event A is getting a green on the first spin. And that's this column. It's been highlighted in green for us. So we can either get first a green and then a red, first a green and then a yellow. Both of them are green, or first a green and then a blue. Event B is getting a yellow on the second spin, and that's been highlighted in yellow for us. A union B is getting a green on the first spin, or a yellow on the second spin, or both, okay? So that is everything that's been highlighted in green or yellow or both colors. And it says verify the following. The number of elements in the sample space is 16. So notice the sample space has actually been listed here for us. We have 4 columns and 4 rows. So that will be 16. And I've gone ahead and listed out the elements in the sample space, and there are 16 of them. Next, it says verify that the number of elements in event A is 4. And event A was getting a green on the first spin. And there are 4 different outcomes in that event. And then we need to verify that the number of outcomes in event B is also 4. And event B was getting a yellow on the second spin. And there are 4 of those. I've gone ahead and listed them. We can count them. There are 4. Then it says that we should verify that the number of elements in A union B is 7. And if we count, there are 7 elements in A union B. Next, we want to verify that A intersect B contains one element. A intersect B, that was getting a green on the first roll and a yellow on the second roll. There's only one way for that to happen. It's right here. And so there is only one element in that event. Next, we're supposed to verify that the probability of event A is 4 out of 16. And the way we compute a probability, is the number of elements in the event divided by the number of elements in the sample space. And there were 4 elements in the event, and there were 16 elements in the sample space. So that gives us 4 out of 16, and we could reduce that down to 1/4. Next, we're supposed to verify that the probability of event B is also 4 out of 16. So the way we find the probability of event B is we take the number of elements in B and divide by the number of elements in the sample space. There were 4 elements in event B, and there were 16 elements in the sample space. Remember, the sample space was just all 16 of these. Next, we're supposed to verify that the probability of A union B is 7/16. And the probability of A union B is the number of elements in A union B divided by the number of elements in the sample space. And there are 7 elements in A union B, so that does give us 7/16. Next, we're supposed to verify that the probability of A intersect B is 1/16. The probability of A intersect B is the number of elements in A intersect B divided by the number of elements in the sample space. And there is just one element in A intersect B, so that does give us 1 out of 16. Anybody have any questions so far? Okay. So this problem continues. It says, next, we need to show that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of that intersection. And the probability of A union B, we found, was 7/16, and that is equal to 4/16 plus 4/16 minus 1/16. So it is equal to the probability of A plus the probability of B minus the probability of their intersection. And it says, apply this to find the probability of A union B in the following cases. So now we have a new event A. Event A is the event of getting a red on the first spin. And that's going to be this first column here, okay? And then B is getting the same color on both spins. So B is going to be that both spins are red, both spins are yellow, both spins are green, or both spins are blue. The probability of A is the probability of getting a red on the first spin. So we could have red, 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 yellow, red, green, or red, blue. And there's 4 outcomes in that event out of 16 outcomes. So that probability is 4/16. The probability of event B is the probability of getting the same color on both spins. And that's the probability of getting red, red, yellow, yellow, green, green, or blue, blue. And that's 4/16 also. The probability of A intersect B. So now we want to think about the intersection of these 2 events. And that's the probability of getting a red on the first spin and the same color on both spins. That means that we would have to just get red, red. And so there's 1 outcome out of all 16 outcomes. So that probability is 1/16. Next, we want to do the probability of A union B, Okay, so that's getting a red on the first spin or getting the same color on both spins. But we're going to use the formula that we just saw. Okay, so we have the probability of getting a red on the first spin or the same color on both spins. That's equal to the probability of A plus the probability of B minus the probability of their intersection. And the probability of A, that was 4/16. The probability of B was also 4/16. And the probability of the intersection was 1/16. If we add 4/16 and 4/16, we get 8/16. And then we're going to take 8/16 minus 1/16, and that gives us 7/16. Next, we're going to look at event A being getting a yellow or a blue on the first spin. So yellow on the first spin, there's 4 of those. Blue on the first spin, there's 4 of those. Event B is getting a red or green on the second spin. So red on the second spin is here. Green on the second spin is here. The probability of event A, that's the probability of getting a yellow or a blue on the first spin. And that's the probability of these 8 different outcomes. So that would be 8/16. I've reduced that down to 2/4. We also could reduce it down to 1/2. The probability of event B, that was getting a red or a green on the second spin. Okay, so we have 4 outcomes with a red on the second spin and 4 outcomes with a green on the second spin. Okay, so there's 8 outcomes. And so that gives me a probability of 8/16, which reduces to 2/4. It would also reduce down to 1/2. And the probability of A intersect B. So that's going to be both of these things happening. That's going to be the probability of getting a yellow or blue on the first spin and a red or green on the second spin. So there's not very many ways for that to happen. We could get a yellow and a red, or a blue and a red, or we could get yellow and green, or blue and green. So there's only 4 outcomes out of the 16 possible outcomes. And that reduces down to 1/4. Okay, so we've done the probability of A, the probability of B, the probability of A intersect B. Next, we're going to do the probability of A union B. And that's getting a yellow or blue on the first spin or a red or green on the second. And we can use the formula for that. That's the probability of A plus the probability of B minus the probability of A intersect B. So we have the probability of A plus the probability of B minus the probability of their intersection. So we have 2/4 plus 2/4 minus 1/4. If we add 2/4 plus 2/4, that gives us 4/4. And so we do 4/4 minus 1/4, and that gives us 3/4. Any questions about anything so far? Okay. For number 19, it says, for the experiment in exercise 18, where a spinner is spun twice, consider the following events. Event A is getting a blue on the first spin. So that would be this column right here. Event B is getting a yellow on one spin. Event C is getting the same color on both spins. Describe the following events and find their probabilities. A union B, that would be getting a blue on the first spin or a yellow on one spin. So we could have blue red, blue yellow, blue green, blue blue. We could have a yellow and then a red. Now this one, I wasn't quite sure if I should consider it to be part of the event or not. So event B was getting a yellow on one spin. I wasn't sure if they meant at least one spin or exactly one spin. They could have been a little bit clearer on that one. I decided to go with at least one spin, so I included yellow, yellow. And then I also have a yellow, then a green, a yellow, then a blue, and then I would want red and then yellow, green and then yellow, okay? So red then yellow, I've already included yellow, yellow, green and then yellow, and I've already included blue and then yellow. So I've got all of those. To find the probability, I need to count up how many there are. There were 10 of them out of 16, and that reduced down to 5/8. Part B was event B intersecting event C. So event B was getting a yellow on at least one spin and getting the same color on both spins. So that would be, you have to get yellow on both spins, yellow, yellow. Next, we're gonna find the probability of that. So the probability of B intersect C is the probability of getting yellow, yellow. And since there's only one outcome out of 16 outcomes, that's 1/16. Part C of the problem, B complement. Well, since B was getting yellow on at least one spin, if that didn't happen, that means we didn't get yellow on either spin. And so I've listed out the possibilities where neither spin was yellow. So both are red, or we have red and then, or green and then red, blue and then red, red then green, both green, blue then green, red then blue, green then blue, or both blue. And so the probability of that happening, I need to count up how many of those there are, and there are 9 of them. So the probability is 9 out of 16. So notice that the probability of B complement is equal to 1 minus the probability of B. So if we counted up the number of spins that have at least one yellow, we have 1, 2, 3, 4, 5, 6, 7. So the probability of B would be 7 out of 16. And we can see that the probability of B complement is 1 minus 7 out of 16. So this is going to bring us to some properties about probabilities. For any event, the probability of the event is going to be a number between 0 and 1. A probability can never be negative, and it can never be larger than 1. The probability of an event that's the empty set will be 0. And the probability of the whole entire sample space is 1. Something in the sample space must happen, because the sample space is just a list of all the possible outcomes. For all events A and B, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of their intersection. And we saw that in problem number 18. And if A bar denotes the complement of event A, then the probability of A bar will be 1 minus the probability of event A. Next, we're going to look at problem number 20. A student is selected at random. Let A be the event that the selected student is a sophomore, and B be the event that the selected student is taking English. Write in words what is meant by each of the following probabilities. The probability of A union B. Okay, union means or. So this is the probability that the selected student is a sophomore or taking English, or both. Okay, remember when we do union, we always include the possibility of both. The probability of A intersect B. Okay, this is where we're going to look at the overlap of the two things. We're going to do and. So this is the probability that the selected student is a sophomore who is taking English. So both things are happening. 1 minus the probability of A. Okay? So from the previous slide, we know that 1 minus the probability of A is equal to the probability of A complement. Since A is that the student is a sophomore, A complement means that the student's not a sophomore. So 1 minus the probability of A is the probability of A complement, and that's the probability that the student is not a sophomore. Number 21 asks, what is false about the following statements? Part A, the probability that it will rain today is 20%, and the probability that it won't rain today is 60%. Well, the sample space, all the possible outcomes, it either rains or it doesn't rain, right? And we need the probability of the sample space to equal 1. So if we add up the probability that it rains plus the probability that it doesn't rain, that has to equal 1. But if we add the 20% and the 60%, we only get 80%. Part B, since a deck of cards contains some face cards and some non-face cards, the probability of drawing a face card is 1/2. Well, if there are only 2 outcomes, the probability of each outcome is 1/2, but only if and only if those outcomes are equally likely, okay? And it's not equally likely that a card is a face card or non-face card. There are many more non-face cards than face cards. So those outcomes are not equally likely. The probability that I get an A in this course is 1.5. Well, remember, all probabilities must be between 0 and 1. It's not possible to have a probability that's larger than 1. Okay, number 22 says 2 fair 6-sided dice are rolled and the sum of the dots on the top faces is recorded. So here are the possible outcomes. This is straight from your book. And then we've added up. So if both dice give us a 1, that adds up to 2. That's the only way to get a 2. Part A was to complete the table. Well, only the first 2 are given to you. I've gone ahead and completed it already. There's only one way to get a sum of 2. There are 2 ways to get a sum of 3. There are 3 ways to get a sum of 4, and so on. There's only one way to get a sum of 12. That's if they're both 6s. Use the table to find the probability of the following events. Event A, the sum is prime. Well, if you roll and the sum is prime, then you must have gotten a sum of 2 or 3 or 5 or 7 or 11. So I figured out how many ways there are to get a sum of 2, 3, 5, 7, or 11. I know there was 1 way to get a 2, 2 ways to get a 3, 4 ways to get a 5, 6 ways to get a 7, and 2 ways to get an 11. And there were 36 different outcomes in the sample space. So that was 15 out of 36, which reduces down to 5/12. Okay. Part B, we want to figure out the probability that the sum is a divisor of 12. So the divisors of 12 that we could roll as the sum are 2, 3, 6, and 12. So I know there's 1 way to get a 2, 2 ways to get a 3, 5 ways to get a 6, and 1 way to get a 12. So that gave me a probability of 9 out of 36, which reduced down to 1/4. Part C, the sum is a power of 2. Well, the powers of 2 that you could roll as the sum are 2, 4, or 8. There was 1 way to get a 2, 3 ways to get a 4, and 5 ways to get an 8. So this gave me a probability of 9/36, and 9/36 simplifies down to 1/4. Part D, the sum is greater than 3. If the sum is greater than 3, it must have been a number between 4 and 12. And so I added up the different ways to roll a number between 4 and 12, and that gave me 33 out of 36, which reduced down to 11/12. We could have also used the complement. So the complement of rolling a sum greater than 3 is that the sum is less than or equal to 3. So the sum was either 2 or 3, and there were 3 ways to do that. So we could have done the probability of getting a sum greater than 3 as 1 minus the probability that the sum is less than or equal to 3. And so that would be 1 minus 3/36. That would give you 33/36, or 11/12. Problem number 23 says the probability of a geometric event involving the concept of measure, length, area, and volume is determined as follows. Let M of A and M of S represent the measures of the event A and the sample space S. The probability of A is the measure of A divided by the measure of S. For example, in the first figure, if the length of S is 12 centimeters and the length of A is 4 centimeters, the probability of A would be 4/12, or 1/3. Similarly, in the second figure, if the area of region B is 10 square centimeters and the area of region S is 60 square centimeters, the probability of region B is 10/60, or 1/6. So if we have a bus that travels from Albany to Binghamton, a distance of 100 miles, if the bus has broken down, we want to find the probability that it's broken down within 10 miles of either city. Okay, part A, the road from Albany to Binghamton is the sample space. What is M of S? M of S is the total distance, which is 100 miles. Event A is that part of the road within 10 miles of either city. So either 10 miles from Albany or 10 miles from Binghamton. So the measure of A is a total of 20 miles. Find the probability of A. Well, we take M of A over M of S, so that's 20 out of 100. We could say that's 1/5, or 20%. Next, we're going to look at number 24. It says the dartboard illustrated is made up of circles with a radius, the small one of 1, the next one of 2, the next one of 3, and the large one has a radius of 4. A dart hits the target randomly. What is the probability that the dart hits the bullseye? So I'm going to assume that it will hit somewhere within the biggest circle. So the entire sample space is the total area of the largest circle, which is 16 pi. Event A is hitting the bullseye in the middle. The measure of A is the area of this small circle, which comes out to be 1 pi. The probability of A is going to be the measure of A divided by the measure of S. So we have 1 pi over 16 pi, and that reduces down to 1/16. Did anybody have any questions about anything? Okay, well, that is it for today. So if you guys don't have any questions, we're gonna stop our meeting, and we won't have a virtual class tomorrow. The next one will be on Monday, and we're gonna be looking at section 10.1, and that's going to be about looking at data and making graphs. Feel free to send me an email if you have any questions about anything. All right. I'll see you on Monday.
Thank you.
Thank you.
Thank you.
All right. Glad you could make it. See everybody next time.